Okay, then we go to the last relation. Now we are going to go in deep, or almost in deep, in the technology. I hope not too much in deep, okay? State of art and potential of the available gas absorption heat pump technology. Marco Guerra is a very well-known absorption technology expert. Is going to illustrate how this technology works, and I think also some possible development for the future.
Yeah.
Please, 20 minutes.
Before entering the presentation of the gas absorption technology in the heating applications, let me outline some very basic features of a gas absorption heat pump versus a regular boiler or versus a regular compression heat pump. Okay, in a boiler, the input is heat obtained, for example, from combustion, and it is released as useful output heat. For example, to the water loop of a hydronic heating system. The amount of output heat is the same amount of the heat input minus, for example, the flue losses, and can never exceed the heat input. Very simple. You put inside 100, you get maximum something less than 100. And if you talk about a regular or a compression heat pump, we have a device in which mechanical energy drives a thermodynamic cycle to pump heat from a low temperature source, a renewable source, for example, outdoor ambient air, to a higher temperature sink, for example, the water loop of a hydronic heating system. The output heat is the heat pumped from the low temperature source plus the mechanical energy input. And this is the gas absorption heat pump. It's a device in which heat, not mechanical energy, heat drives a thermodynamical cycle to pump heat from a low temperature source, for example, outdoor ambient air, to a higher temperature sink, for example, the water loop of hydronic heating system. When applied to an heating system, a gas absorption heat pump device delivers the heat output at an efficiency much higher than a conventional gas boiler. And the useful output heat is the sum of the heat input plus the heat pumped from the low temperature source minus the flue gases. The useful output heat is higher than the driving input heat. While in a conventional boiler, the useful output is always lower than the input. So this is to generally depict how this different technology works and the energy fluxes. In the previous speech, we have seen that several new European initiatives have already recognized in the various heat pumps technology, and specifically in gas absorption heat pump, the potential to address a significant reduction in energy consumption. New heat pump heating systems are capable of achieving energy savings up to 50%. Most European countries already consider the heat pump as the next step after the condensing boiler in achieving higher efficiency in new buildings. This is a technology ranking done by the European Commission, and at the A, we see the best condensing boiler, classified as A, and we see at the same level heat pump, air source means the renewable is outdoor air, heat pump, compression heat pump, mechanical energy-driven heat pumps. But at a higher level, we found ground source mechanical-driven heat pumps, which means geothermal electrical heat pumps, but also the best gas absorption heat pumps. They have been already recognized as the maximum energy efficiency possible technology. So this scenario is extremely favorable, but a number of technological and non-technological issues need to be addressed carefully to make the heat pumps, in general, a viable product for the market. And in this speech, I will focus primarily on the technological issues. When dealing with heating and domestic hot water in Europe, it's important to highlight that the residential market is roughly 90% of total sales. In this large share, roughly 95% is retrofit or replacement market, which basically means hydronic systems based on radiators and with heating water temperatures in excess of 70 Celsius. And this is the legacy of the existing European building stocks, as we have seen, resulting from decades of application of gas boilers. So, in the retrofit application, that is where the highest demand for the improvement exists, we found the significant challenges for the various heat pump technologies. Big challenge for the heat pump. And I would like to highlight some of these challenges, in particular for residential application. First of all, the access to a low temperature source. There are several options: outdoor air, geothermal heat, winter solar panels, groundwater, and combination of the above. This is something which is not need in gas boilers, but we have to with heat pumps. Radiators impose water temperature in excess of 70 Celsius. Modulation of heating capacity. Typical residential boilers' maximum capacities are around 20 kilowatts, roughly, which can be modulated down to 4 kilowatts in the best design condensing boilers. The maximum output is normally delivered only during those very few hours per year when the outdoor temperature reaches its lower level. Of course, availability of domestic hot water. The system must be able to provide domestic hot water as a complementary service, like a regular boiler does. Ease of installation. The average installer must be able to correctly install and service the product. The location of the device should either exactly replace an existing boiler or fit within given typical appliance dimensions. Outdoor installation could be an advantage, but it is not always available or possible. Okay. Low noise level. Boilers have already established in the mind of consumers a very high expectation for quietness of the heating function. High efficiency, of course, operation, but the efficient performance must be assured with a simple system of control, enable simpler user interface. Not sophisticated controls will be accepted by the installer and by the end user also. And low emissions, of course, reduce amount of direct and indirect emissions, in particular in urban areas, CO2, NOx, and PM. And finally, the availability of technology at a price level that will encourage end users to upgrade, either because short payback time versus regular boilers, or because lower required investment than alternative renewable heating solutions. So these are the challenges for the heat pump. Let's now review some general consideration about heat pumping technology and the way it can address these challenges. The first one is how we get the renewable source. For a residential retrofit application, the only viable renewable source choice is outdoor air, with possible support of solar heat. Drilling geothermal wells or using groundwater is possible for new buildings, but only in corner case conditions for existing building. The geothermal installation itself will raise the cost of a heat pump system far above any other alternative. Current status of heat pump technology implies that temperature in excess of 70 can be reached only by means of water ammonia absorption, CO2, or two-stage compression system with a possible choice of alternative refrigerant. But also, combination of high temperature heating water with low air source temperature while providing full capacity is possible with absorption technology or with compression heat pump plus backup boiler combination. Modulating capacity is also a mandatory feature, and it's already available on gas absorption heat pump and on heat pump also. Okay. Then, the installation and size is a common challenge for most heat pump systems. Very difficult exactly fit within the typical boiler location and dimensions. By the way, new heat pump design are available, allowing more compact and lower weight units, and the target of 10 kilograms per kilowatt output is already conceivable. The noise and auxiliary energy consumption of future heat pump could take advantage of the latest development in acoustic insulation, fan blade geometry, high efficiency inverters for fans and water circulators. And finally, the cost of heat pumps in general will be higher than a plain boiler, of course. It's more complicated inside. But the potential for a significant difference reduction is in large volume manufacturing. So, let me now focus on specific consideration about gas absorption heat pump, not in heat pumping in general, so the peculiar absorption technology. And these elements contribute to make the water ammonia air source modulating gas-fired heat pump as one of the most promising technologies for the next steps in energy efficiency improvement. First of all, existing gas absorption heat pumps already provide among the highest efficiencies available in heating system. The technology is based on natural refrigerant, water, and ammonia. The ODP is zero, the GDP is zero. Direct and indirect emissions are, according to the latest data published by the European Commission, when taking in consideration all emission factors, CO2, NOx, and PM, already outstanding as the cleanest solution for the heating application. Gas absorption heat pump are gas-fired, can be air source and yet maintain its high efficiency, and deliver high water temperature. This makes the application of gas absorption heat pump very similar to regular boilers from capacity, temperature, and controls point of view. The thermodynamic cycle is hermetically sealed and substantially static. A solution pump, which reduced to two check valves and a membrane, are the only mechanical moving parts. And this is for long life of the system and service-free operation of the cycle, which is required in heating application. Okay, gas absorption heat pumps are already industrially manufactured and benefit from the long experience of the absorption chiller industry. The cycle components are steel made versus the copper-made compressor component. This requires a specifically developed component design and manufacturing process, which is a technology barrier, of course. But once developed, there's a high potential for manufacturing cost reduction. The steel-based material ranging from 1/5 to 1/8 of the copper-based material cost, which is a lot. Gas absorption heat pumps are gas-fired, so do not add load to the electrical grid and therefore impose neither the creation of smart grid to manage the incremental loads, nor the upgrade of the generation and transmission system to deliver the extra capacity. The principle of absorption thermodynamic has been known since the late 1800s, but the potential for new development gas absorption heat pump technology is huge. Only few manufacturers and university research labs have recently investigated on this technology. What would happen if even a small portion of the effort that has been devoted to boilers or compressor R&D would be addressed to this technology? The gas absorption technology has already reached an efficiency, a GUE, of 160%. Potential efficiency increase up to 190 and more are already possible with advanced cycle design. There is already a large number of novel advanced absorption cycle theory available. A lot of these new cycles never really fully simulated and experimentally developed. And finally, the skills required for a gas absorption heat pump technology range from thermodynamic systems to chemistry to heat and mass exchanger simulation to fluid dynamics to metallurgy, etc. The jobs created for such development are high education, training, and expertise requiring. They will form a core competence team that will add value to the entire organization investing in them. In conclusion, we have seen here the key challenges for the retrofitting and the key and unique benefit of the gas absorption technology can bring to address these issues. But also let me add some extra feature, some consideration about further potential of the ammonia water absorption cycle as a fallout of the technology in other field of application, completely different. Water ammonia absorption technology is the base for new multi-stage cycle that can be driven by low temperature waste heat to deliver free air conditioning or refrigeration. I am personally following the development of an air-cooled refrigeration prototype using a pure water and ammonia dual lift absorption cycle driven by hot water from 70 to 95 Celsius. And this new absorption development concept could offer several new opportunities, including automotive air conditioning or truck refrigeration when used in combination with engine cooling tower, air conditioning application without cooling tower, driven by low temperature solar system or biomass boilers, air conditioning application based on district heating networks, through generation application for the growing market of high efficiency combined heat and power. And then, different consideration again. Maybe some of you are already familiar. The water ammonia absorption technology is the base for the Kalina family power cycles, which is the most efficient alternative to the Rankine cycle up to date. And the Rankine cycle means 60+% of energy production in the world today. So the same base technology. So in conclusion, the research and development of gas absorption heat pumps technology offer the heating industry a unique opportunity for providing a significant energy saving in the European heating and domestic hot water market, providing a range of high efficiency product fitting into the real and most demanding marketplace, the retrofit you have seen, to help shifting the excess manufacturing capacity of the heating industry towards a high-tech industrial environment, creating highly qualified jobs and new proprietary core competence teams, and explore other significant possibilities offered by the same core-based absorption technology.